physics. So this is the outline of the talk, and I will start with a very brief introduction concerning neutrino interactions with nuclei, and then I will discuss the process that is the main topic of this seminar, which is CEvNS. I will discuss its main features, and then I will also comment about which experiments are capable of detecting CEvNS and have actually already observed this process. And then I will move to the main part of the seminar, which is about the phenomenology of CEvNS and its physics implications, as I said before, both concerning standard model and new physics. So we know that neutrinos are elusive particles, but they are not completely unfriendly because they do talk with other standard model particles via weak interactions, in particular via charge current and neutral current processes. So in this seminar, I will discuss CEvNS, which is a neutral current process, as we will see. And it's about neutrino interact with nuclei. So depending on the energy of the neutrinos, they can undergo different processes of interactions with nuclei. In particular, if neutrinos are very energetic with energy above, let's say, the TeV scale or so, they would undergo deep inelastic scattering with nuclei, and this is a process that would literally blow up the nucleus, and it's, let's say, the most destructive of all the possible interactions of neutrinos with nuclei. Neutrinos, which are a bit less energetic, with energies around the GeV scale or so, would start feeling the interactions with nucleons inside the nuclei, but these processes could also be disruptive and sometimes leading to the production of new particles. Less energetic neutrinos with energies below the GeV scale or so would instead have interactions with nuclei and electrons inside the nucleus, and this process would already be minimally disruptive of the nucleus itself. And finally, neutrinos with energies below, let's say, tens of MeV or so, are those that would induce coherent elastic neutrino-nucleus scattering. That is the process that is the main topic of this seminar, and it is the gentlest of all these possible neutrino interactions with nuclei. So let's have a look at which are the main features of CEvNS. So coherent elastic neutrino-nucleus scattering is also called CEvNS from its acronym in English. And it's a neutral current process in which a neutrino scatters off a nucleus by the exchange of a Z boson within the standard model. It is coherent because the amplitudes of the neutrino scattering on individual nucleons edge, and it is elastic in the sense that no new particles are produced, and the nuclear target remains in the same energetic state, so in the ground state, after the interaction. In this process, the neutrino sees the nucleus as a whole, as a single particle, and this leads to a typical enhancement of the CEvNS cross-section, which eventually turns out to scale approximately with the number of neutrons squared. So the CEvNS cross-section can be quite large, for instance, a couple of orders of magnitude larger than the inverse beta decay one, which was first used to observe neutrinos. CEvNS was first theoretically predicted in the 70s, in particular in this paper by Friedman, where he defined it as an act of hubris in the sense that he understood right away that experimentally would be very complicated to observe CEvNS because the reaction product would be a nuclear recoil of very low momentum, and therefore very, very difficult to detect experimentally. Indeed, it took more than 40 years for the CEvNS process to be observed, for the first time in 2017 by the Coherent experiment in the US. So CEvNS is indeed an exceptionally challenging process to observe because despite the magnitude of its cross-section leads to very tiny nuclear recoil energies. So this figure on the left shows the typical magnitude of the CEvNS cross-section in red compared to, for instance, the inverse beta decay neutrino cross-section. Also, let me notice that the CEvNS process has no energy threshold, contrary, for instance, to the inverse beta decay, whereas the figure on the right shows the typical n-square dependence of the CEvNS cross-section together with the sum of the current measurements of the process and some upper limits on this cross-section that have been set by different experiments that I will now discuss in more detail. So just to understand a bit more, the characteristics of CEvNS and going back to neutrino nuclei scattering. So as I was saying, neutrinos can undergo different processes in the scattering with the nuclei depending on their incoming energy. And here we are interested in a process which is a neutral current one, so it is mediated in the standard model by the Z boson. So the processes that the neutrino nucleus scattering processes can be different depending on the wavelength of the mediator, in this case of the Z boson. So when the wavelength of the exchange, the Z boson, is smaller than the nuclear radius, then the Z boson has a high probability of interacting with a single nucleon inside the nucleus, leading to its ejection. And then we would be in the regime of inelastic incoherent scattering. When the wavelength is smaller but also comparable to the nuclear radius, then the Z boson would have a high probability of interacting with a group of nucleons. So we would be, let's say, in an intermediate regime. And finally, when instead the wavelength is larger than the nuclear radius, or said in other words, when the momentum transfer in the process is smaller than the inverse of the nuclear radius, then we are in the regime of CEvNS, which is the elastic coherent one. We can also estimate the typical magnitude of the momentum transfer, for instance, for a heavy target nucleus like cesium, which is the target material that was used to first observe CEvNS. And we see that this momentum transfer is of the order of 35 MeV or smaller. We can also estimate the maximum nuclear recoil that is expected in this process, and this was done already in this paper from the 80s, for instance. And this recoil energy depends, of course, on the energy of the incoming neutrino and on the mass of the nucleus, so on the target material. So, for instance, for neutrinos from accelerators, we would expect nuclear recoils with energies below 10 keV or so, and we would be close to the decoherence regime. Whereas for neutrinos produced from nuclear reactors, we would expect recoil energies of the order of 100 electron volt or smaller. And here we would be in the case of full coherence. So now that we have seen the main features of the CEvNS process, let's see which are the experiments that can try to detect it and which are those that I've already observed it. So let's start discussing the neutrino sources that can produce neutrinos with the energies typical for the CEvNS process to occur. So neutrino sources that are good to induce CEvNS are those that have some preferable requisites, in particular a high flux, of course, a well-understood spectrum, ideally the possibility of producing different neutrino flavors. CEvNS is a neutral current process, so it's flavor blind, but having different flavor components in the neutrino source can be helpful at the scope of some BSM probes. And also the possibility of locating the detector close to the source can be useful in the sense that this would enhance the flux. And of course, a good knowledge of backgrounds and the possibility of rejecting most of it. So we can have sources that can comply with these requirements, both of natural or artificial origin. Concerning the natural sources, we have neutrinos from supernovae bars or from the diffuse supernova neutrino background, geoneutrinos, and then atmospheric and solar neutrinos, which indeed induce CEvNS, for instance, in Darmstadt direct detection experiments, as we will see. Regarding instead artificial sources, several have been discussed in the literature, the neutrino from stopped pions and from nuclear reactors, neutrinos from radioactive sources, and also next generation neutrino beams, like those that will be exploited, for instance, from the DUNE experiment, could be used for CEvNS, even though they are usually produce neutrinos that are more energetic. The low energy tail of this spectrum could also be used to induce CEvNS. However, most of the current and let's say near future CEvNS experiments use neutrinos from these two sources, from stopped pions and from nuclear reactors. So let me discuss them in more detail. In particular, let me start with neutrinos from PIDAR, from pion decay at rest. This is the source, for instance, of neutrinos observed by the Coherent experiment. So here the idea is that we have some protons that is accelerated at the spallation neutron source, and this hits a target. In the case of the Coherent experiment is a mercury target, and here pions are produced. The negatively charged pions are captured right away by the nuclei, whereas the positively charged ones decay at rest, producing a prompt flux of muon neutrinos and delayed fluxes of muon antineutrinos and electron neutrinos. So the typical flux of neutrinos from a PIDAR source is shown in this figure with the three different components. There are different laboratories that can generate at present these neutrinos, like the spallation neutron source, which is the one used by the Coherent in the US, another one also in the US at the Lujian Center, one in China, and there is the European spallation source under construction in Europe. So this source is characterized by a high energetic flux. It's a pulse beam, so this information can be used to reject at least part of the backgrounds, although backgrounds from neutrons are usually very large, and so they have to be treated carefully. Also, as I was saying before, there is an important timing information in this kind of source, because one of the flux component is prompt, whereas the other two are delayed. And so also this piece of information can be used to reject backgrounds, or in some BSM sources to disentangle the neutrino signal from some other BSM signal. Then most of other CEvNS experiments use a different kind of neutrino source, which are neutrinos from nuclear reactors. In this case, the advantages are that nuclear reactors are a copious source of electron antineutrinos, and these neutrinos have a lower energy compared to the accelerator ones, so the coherency condition is largely preserved. But the disadvantages of these, let's say, these experiments are that the recoil energies that are induced in the process are even smaller, so even more complicated to observe. Backgrounds can also be important here, although the reactor off period can allow to measure them. And only one flavor is accessible, only the electron one. So the typical neutrino flux expected from nuclear reactor as a function of the neutrino energy is shown in this other figure. So we have discussed now the sources that can produce neutrinos with energies of the MeV scale or so that can induce CEvNS. Let's see which are the experiments that can try to detect it. So as can you see, as we can see, these experiments need to observe some very tiny recoil energy, so they face the same problems faced by Darmeder direct detection experiments. And indeed, the detection strategies are in common with these Darmeder facilities. So in general, the point is that we need to translate these small recoil into something visible that can be light, charge, or heat. So photons, ionization, or phonons. And of course, so experiments will rely on one of these detection strategies, or also they can combine two of them at the same time. There are several experiments that are currently running worldwide. So this map summarizes most of them, or also some that are in construction, so are planned for the near future. And also this map shows them characterizing them in terms of the neutrino source. So as I said before, either stopped pion beams or nuclear reactors. I will now discuss in more detail some of them, in particular the Coherent experiment, which is the one that first observed CEvNS. So indeed, let's see which are the experiments that have observed CEvNS. So the first observation was made by Coherent in 2017 using a detector made of cesium iodine. And let me notice that it was basically the smallest working neutrino detector of only 14 kilograms, which is quite impressive for a neutrino experiment. But given the magnitude of the CEvNS cross-section, this volume was enough to observe the process. And indeed, the observation was made at 6.7 sigma confidence level. Then the same collaboration took more data using the same detector, and in 2021 they released an extended data set, also improving the statistical analysis, and eventually they rejected the no CEvNS hypothesis at 11.6 sigma level. Meanwhile, the Coherent collaboration wanted to use different target materials really to explore this typical n-square dependence of the cross-section. So meanwhile, in 2020, they also observed the process using a different target, liquid argon. Again, it was a kind of small neutrino detector, only 24 kilograms. The statistics here of this result is a bit lower compared to the cesium iodine one, but it was the first confirmation of the n-square dependence of the cross-section. Now, recently, actually this year, at the Magnificent CEvNS workshop in Valencia, the Coherent collaboration announced the measurement of CEvNS also using a third detector made of germanium. Again, a small system. However, they are working in some upgrades of these detectors, both the liquid argon one, the germanium. So at present, this observation is at only almost 4 sigma level, but of course we are waiting for more data in the near future. So as you can see now, this figure that I showed before of the typical n-square dependence of the cross-section, there are now 3 points that are trying to reconstruct this curve. So concerning reactor experiments, at present, let's say none of them has really observed the process apart from this claim by this experiment using reactor neutrinos from the Dresden 2 reactor in the US. Other experiments like CONUS and CONI have already released very interesting results and set some upper limits on the cross-section, but they did not really observe the process. In 2022, this collaboration released this paper where they claim this evidence of suggestive evidence of CEvNS that they report with strong preference with respect to the background-only hypothesis. So this detector is interesting because it's a germanium one, and it is characterized by a low energy threshold. And as I was saying, this experiment uses neutrinos from a nuclear reactor. However, the interpretation of this result in terms of CEvNS observation is very strongly dependent on the quenching factor model. So experiments that relies on ionization, but also on scintillation, they need to use this quenching factor, which is basically a quantity that describes the observed reduction in ionization yield produced by a nuclear recoil when we compare it to an electron recoil of the same energy. Basically, this quantity tells us that not all the recoil energy, nuclear recoil energy, is in a readable format. So the quenching factor is defined as a ratio between the measured energy, recoil energy, and the theoretical expected nuclear recoil energy. So it's a factor that basically reduces the energy that we are capable to observe. So this figure on the right shows the typical the values of this quenching factor for a germanium target, like in the case of this experiment, and NCC 1701, as a function of the nuclear recoil energy. And as you can see, these 3 different colored curves correspond to 3 different parameterization of this quenching factor. So when we extrapolate them at low energy, there are huge differences between the expected values. And so the interpretation of this result of this experiment in terms of an observation relies on the choice of this quenching factor model. So only when we choose the quenching factor that leads to the larger value at small energy, then let's say the data are compatible with an observation of CEvNS. The point is that this result is not really in agreement with some other experiments like CONUS, which is also a CEvNS experiment that uses neutrinos from nuclear reactor. And in particular, the measurement of this quenching factor is not really in agreement. So there is still some controversy behind this result, and the community is waiting for more results and more observations from other reactor experiments to clarify the situation. Now, this year was actually quite exciting because besides, the third measurement of Coherent, there were this summer, there were 2 claims of observation also from dark matter direct detection experiments, in particular Xenon and TON, that announced at the IDM conference in Italy that they observed 7 signal in their xenon detector induced from solar boronate neutrinos. The significance of this result is still low, below 3 sigma, but of course it's extremely interesting because it's the first detection of this kind by this kind of experiments. Then just after this announcement, the Panda-X collaboration, the Chinese experiment, also published a paper where they also announced that they reject the background only hypothesis at, let's say, almost 3 sigma significance. So this means that these experiments are really already, let's say, I mean, the CEvNS process it's already accessible also using these dark matter experiments. So this is very, very interesting. Okay, so let me now discuss, let's say, the main part of the seminar, which is about the implications of CEvNS. So let's start with the standard model, and let me start with the standard model cross-section. So the CEvNS cross-section is well calculable in the standard model, and in full generality contains 2 contributions, a vector and an axial vector one. However, the axial contribution is spin dependent, and it is small for most nuclei, especially for the very heavy ones that are those that are in general used by these experiments. So we can safely neglect it. And we can focus on the vector part, which is shown here, and which depends on, the Fermi constant, which is a standard model parameter, a kinematic term, a nuclear force factor, which is approximated to 1 in the case of full coherence, so when the momentum transfer is very small or close to 0. And this extra term, which is the weak nuclear charge, which is defined here, which is the term that eventually encodes the typical n-square dependence. Indeed, we can see that the number of protons, Z, is multiplied times this factor, which depends on the value of the weak mixing angle. And given the value of the weak mixing angle within the standard model, this factor basically cancels out. And so that's why we are left with the typical n-square dependence of this cross-section. So the observation of CEvNS has really opened the window to a plethora of possibilities concerning the implications of this process. I will try to discuss some of them. For the sake of time, I will not be able to go through all of them, but let me start with the electroweak precision tests, so standard model probes. So let me show again this differential CEvNS cross-section for the standard model. Basically, the standard model physics enters through this term, that is the weak factor, as I said before, the weak charge, and which is the one that encodes the n-square dependence. So this is the term that encodes the information on the value of the neutrino-neutral current interaction at low energy through the weak mixing angle. And indeed, this is the observable that we can try to extract from CEvNS data. So the point is that, of course, we have good measurements of the weak mixing angle at high energies from collider data, but we do not have many at low energies, at energies typical of the CEvNS process. So we can, of course, extrapolate the value from higher energies using the RG running, but of course it's also interesting to confirm the expected value, the theoretical expected value with the experimental data, because any possible departure from this theoretical value would be a hint of the existence of some new physics. A variation in the value of the weak mixing angle would affect the normalization of the CEvNS spectra. So since the very first observation of CEvNS by Coherent in 2017, people have already analyzed the data, the CEvNS results, to extract the best fit value of the weak mixing angle together with its uncertainty, like in these two publications here. In this figure on the right, I'm showing the running of the weak mixing angle as a function of the energy scale. So the blue line corresponds to the expected RGE running. And the green lines, the green points with the error bars correspond to the extracted value from the analysis of coherent liquid argon or cesium iodine data. Whereas in red, I'm showing the expected value together with the error bars that we extracted analyzing the Dresden 2 reactor data that, as I said before, are very strongly dependent on the quenching factor model. So we see that especially in one of the cases where we choose one of the models, the error bar is still very huge. This other figure here shows the same, but with some prospects for measurements in the near future, for instance, at a scintillation bubble chamber experiment that is meant to be built in Mexico, and we would use a liquid argon detector. Using the most recent coherent data sets, the cesium iodine one of 2021 and the liquid argon one, we also got some results concerning the best fit value, analyzing the two data sets separately in orange or magenta, or combining the two data sets in blue. So eventually the combined analysis leads to these results shown here on the right, that, as you can see, is of course in very good agreement with the theoretical expected value, although the error bar is of course still quite large, but with more data we expect it to become smaller and smaller. So
Valentina, can I ask something, please?
Yes.
Yeah. So, did you do a combined analysis of the CSI data in that paper? So you combine liquid argon and they combine the two data releases for CSI, right?
You mean the coherent collaboration?
No, the analysis that you were discussing about the weak mixing angle, that analysis. So and there you have three data sets. So you have liquid argon, then you have cesium iodide 2017, and then cesium iodide 2021, right? Okay,
no, we only use the 2021 because it's more complete. It's more complete. It has more data. I mean, it is supposed to include already the 2017 results.
Okay, so everything is included there. Okay, yeah. Thank you.
Okay, so let me continue with some standard model physics that can be studied using CEvNS, in particular nuclear physics. So let me go back to this differential CEvNS cross-section. Now, nuclear physics enters through this nuclear four-factor, which is basically the Fourier transform of the nucleon distribution inside the nucleus. Given the fact that, as I said before, the neutron contribution is more important than protons, basically we can say that the Fourier transform of the neutron distribution is the one that is more relevant or dominates. So the observable that we can extract from this is the nuclear, in this case the neutron, root mean square radius. And this is actually the largest theoretical uncertainty that affects the CEvNS cross-section at present. A variation in the value of this neutron radius would affect the shape of the CEvNS spectra, contrary to what was happening with the weak mixing angle that instead would affect the normalization of the overall spectrum. In order to be able to extract information about this root mean square radius, we need to have some partial coherency. So in this case, an experiment like Coherent is most suited to do it because we need to be in this partial coherence regime. So the CEvNS process can indeed be used to provide a model-independent measurement of this neutron radius. Of course, we need to use some parametrization for the four-factor. And so again, we analyzed the most recent coherent data sets. We fixed the values of the proton radii because these are instead measured quite well using different electromagnetic processes. And in this way, we extracted the best fit value for the neutron radii for the two different targets. In the case of liquid argon, you see that the significance is still very low, so it is actually compatible with 0, but it's just due to the data, let's say. So with more data, of course, we will be able also to extract a better fit for the neutron radius of argon. Why is this interesting? Well, because understanding better the neutron radius has implications for both nuclear physics to understand better the stability of nuclei, and for astrophysics to understand the physics of neutron stars. Okay, now let me instead move to other possible implications of CEvNS concerning new physics. In particular, let me start with the new neutrino interactions. So we know that when we discuss some neutrino models that want to accommodate neutron masses, for instance, often we deal with the introduction of some new interactions. And let's say one of the most studied ones are neutrino non-standard interactions, which are formulated in terms of an effective for fermion Lagrangian, shown in this expression here. Where these epsilons are the NSI couplings that quantify the strength of the new interactions in terms of G Fermi. So basically here, the idea is that we are assuming the presence of some new heavy vector mediator, which is heavy enough to be integrated out, heavy enough compared to the typical momentum transfer of CEvNS, to be integrated out, and therefore to allow us to focus on an effective interaction as depicted in this diagram. So to compute the CEvNS cross-section in this case, we just need to modify the weak charge using this expression here. The weak charge, I remind you, is the one that encoded the n-square dependence. Now we have, of course, also some new parameters, these epsilons that are the NSI parameters that enters now this the expression for the weak charge. So we can again use the data of coherent experiment, and we can extract bounds on the typical NSI parameters. These parameters can be either flavor changing or flavor conserving. So let me start with the flavor conserving ones. So this plot shows the 90% confidence levels preferred region, that are these diagonal colored regions, in terms of the NSI parameters. So the upper panels refer to interaction with electron neutrinos, and the lower ones with muon neutrinos. The plots on the left shows the results when we analyze the two data sets, liquid argon and cesium iodine of 2021 separately, and the right ones instead are what we obtain when we combine the two data sets. So the effect of obtaining two bands is actually expected, in the sense that one of them contains the 0-0 result, which is the standard model one, as we would expect, and the other band corresponds to the case where this NSI cancels the standard model contribution, but the contribution from the NSI mimics the standard model perfectly, basically. Of course, when we have more statistics, so for instance, the muon neutrino contribution to the neutrino flux used by the coherent experiment is larger than the electron one. So you see that already we have the two bands. And when we combine the two data sets, also the allowed parameter space gets reduced. So there was recently a paper on the archive where people have already started to analyze the very recent result of the measurement of coherent using a germanium detector. Of course, when we combine an additional data set, in this case would be 3 of them, the final result is even more constrained, as we would expect. Concerning instead flavor changing NSI, so these are the results given in terms of one flavor changing and one flavor conserving NSI parameter. The shapes are a bit different. Now we don't have the typical bands, we have some circular regions, or eventually a donut shape, let's say. But well, let's say the idea is the same, the message is the same. When we combine the data sets, we get some reduced parameter space, and this recent coherent data allows us to probe these NSI interactions. Next, we can think about doing one step more beyond the typical NSI, which, as I said before, are effective interactions where we assume the presence of a heavy vector mediator. We can go beyond this and consider neutrino generalized interactions, NGI, which could accommodate all possible Lorentz invariant interactions. So now the effective Lagrangian is given by this expression, where now we have a big gamma, which is not only gamma mu, but can encode all possible interactions, scalar, pseudoscalar, axial vector, or even tensor interaction. And now the NGI parameters are these C and D couplings, which are basically the equivalent of the epsilons in the case of NSI, but for these generalized interactions. We can compute the typical cross-sections for CEvNS in the presence of generalized interactions. We have some interference, of course, between the new vector and the standard model in the components, and also between the scalar and the tensor one if they are present at the same time. And we can define some new weak charge associated, for instance, to the new vector interaction, or associated to the new scalar interactions, which comes with the couplings of the new mediator with neutrinos and with quarks, and with some extra information from hadronic structure parameters. And similarly, we can do the same for the tensor interaction. And eventually, then we can again use recent CEvNS data to extract limits, bounds on these NGI parameters, as we have done again here, as it is shown in these figures. The upper panels correspond to the case where we allow for the presence of only one new interaction at a time, whereas the lower panels correspond to the case where we allow for two of them, for instance, tensor and scalar, scalar and vector, or tensor and vector at the same time. So for instance, when we switch on only one interaction, like the vector one, you see here, we get two minima, which is, as we were similar to the NSI case, indeed, where we were getting the two separate bands. So one is the standard model solution. The other one is a solution that mimics the standard model, but with opposite sign. And in between, basically, the new vector interaction cancels the standard model, leading to a very bad fit. In the case of scalar and tensor interactions, when we combine the two data sets, we get that they are perfectly centered in zero. For the liquid argon data sets, the statistics, as I was saying, is still low. So we get two minima, but the significance is very low. So it is not significant. And indeed, the combined analysis is completely driven by the cesium-iodine data set. When we allow for the presence of two interactions at the same time, again, the shapes change a bit more. And of course, we have more allowed parameter space. We have more free parameters. But, the allowed parameter space is either, again, like a circular shape, or is donut shape, or eventually two separate islands when, for instance, the vector interaction is allowed. Okay,
Valentina,
then
can I
yes.
ask something regarding this fit? So, as you said,
Yes.
so the combined analysis is mainly driven by the cesium-iodide data set.
Yeah.
So liquid argon is playing a minor role. What is the reason for that? Because of the statistics, or because of the data quality?
I think at present is just statistics. Indeed, I mean, the results is around 4 sigma, if I remember correctly, for liquid argon, whereas with the new data set of cesium-iodine, they had around 11 sigma of observation, right? So also, I mean, the statistical analysis has been improved with the new cesium-iodine data set compared to the original one of 2017. But the liquid argon one is already quite sophisticated, so I think it's mostly really a matter of data that they have not collected enough yet, you know.
Yeah. Okay.
So that's why you see the shapes are much larger when you analyze the liquid argon alone, or.
Yeah. Okay. So I didn't check for this cesium-iodide last data release, but can you comment on, probably, you know, at the end of your talk, maybe it's probably I shouldn't be asking, but can you comment on how much the quenching factor determination for cesium iodide improved compared with the 2017 measurements that they release?
I don't remember now the numbers, but I think the quenching factor for cesium iodide now it's not a big source of uncertainty. So it's not so relevant like compared, for instance, to the Dresden 2 reactor or to the germanium results of reactor experiments, also because those let's say deal with much lower recoil energies, no?
Yeah.
So I think I don't remember now the numbers, but of course I can tell you
Yeah, sure.
later if you want.
Yeah, thank you. Thank you.
Thank you. Okay, then let me move on. So I've discussed now some effective interactions, NSI, which are vector interactions, and the generalized NGI, which are all possible Lorentz invariant interactions. We can think now about considering promoting these interactions to interactions mediated by light particles, which is, let's say, kind of reasonable for two reasons. First of all, because, well, we need to compare the mass of this mediator to the typical momentum transfer, which is of the order of tens of MeV for CEvNS. So having a light mediator, a mediator with tens of MeV of mass, it's reasonable. And then also because these experiments in particular, the CEvNS experiments in particular, those that use neutrinos from nuclear reactors, are very sensitive to spectral distortions at low recoil energies. And these are this is the signature that we would expect when we consider the presence of some new interactions mediated by a light particle. So we can think about going from an effective interaction like this one to another one as shown in the diagram on the right, mediated by, for instance, a light vector particle. In this case, we need to modify our cross sections. In particular, we will get dependence on the momentum transfer and on the mass of the mediator from the propagator. So, for instance, in the case of a light vector mediator, the CEvNS cross section in this case gets this expression. So it can be given in terms of the standard model cross section, because of course there will be some interference, times some extra term that depends on typical couplings of the new vector mediator with neutrinos and with quarks, and some other factors. It depends, I mean, this term will also depend on a typical model that we want to consider. We consider two of them. One that is called the universal scenario, so in which we basically assume that the mediator couples with equal strengths to the neutrinos and to up and down quarks. Of course, this is just a phenomenological scenario because it would be not anomaly free, but it's useful for phenomenological studies because then the results can be easily translated into more sophisticated models. And then we also consider the case of a full complete model like the B minus L scenario. For the sake of simplicity, because then we can give the results in terms of a single coupling and the mass of the mediator, we define this coupling GV as the square root of the product of the couplings of the mediator with neutrinos and quarks. Okay, let me now comment something else. Of course, all my seminar is based on the CEvNS process, but let me now introduce also this extra process, which is electron-neutrino elastic scattering. Of course, in the standard model, this cross-section, which is, I mean, the cross-section for this process in the standard model is given here. This cross-section is smaller than the CEvNS one when we are at neutrino energies where CEvNS can be induced. But if we consider some BSM scenarios, like the case of a light vector mediator, this cross-section can get an enhancement, which in general it depends on the inverse of the square value of the electron recoil energy. So eventually this cross-section can be large and almost comparable to the CEvNS one. So why we consider this? Because for the cesium iodide data set of Coherent, so the detector is not capable of distinguishing nuclear from electron recoils. And so we had to include the NEUTRINO-NUCLEus events this elastic neutrino electron scattering, because they could induce a signal that could be confused with the CEvNS one. Of course, this contribution is flavor dependent, because in the case of electron neutrinos, we have both neutral current and charge current contribution, whereas for muon neutrinos, which are present in the neutrino source of coherent, only the neutral current is present. So concerning the possible existence of new neutrino interactions mediated by a light vector mediator, we computed here some 90% confidence level exclusion limits in terms of the new vector coupling and the mass of the mediator. For the two models, on the left is the universal scenario, on the right is the B minus L scenario. Again, we analyzed separately the two data sets, liquid argon and cesium iodine, and in blue, we provide the combination of the two. As you can see, in the case of a universal scenario, we have this small island here, which is allowed, and this arises from some destructive interference with the standard model, which is allowed in this scenario, but not in the B minus L one. And then, as you can see here, in the case of cesium iodine, and then of course, this is also translated into the combined result, we have a bump here that basically allows us to restrict smaller values of the coupling at small masses. And this bump really arises from the introduction, from considering the NEUTRINO-NUCLEus events in the analysis. So you see that in these kind of interactions lead to some sizable number of events that also change, let's say, have an effect on the final bounds. Here I'm showing the same results. So on the left, the blue line corresponds to the combined bound that we obtained from the two data sets, again for the light vector mediator. And I'm comparing it to other bounds that exist in the same parameter space, for instance, from collider, beam dumps, CONUS and CONI, which are other two CEvNS experiments that use reactor neutrinos. And then we have Borexino, Darmeder experiments, and of course, well, cosmology, BBN bounds that are relevant, but strongly dependent on the specific model that one would consider. On the right, I'm showing the same, the bounds that we obtained analyzing the Dresden 2 reactor data. As I said before, this result is very dependent on the quenching factor, so we had to choose one of them. But this is just to show how the two results compare, and that there is some complementarity between the different facilities using PIDAR neutrinos, like the case of Coherent, or using nuclear reactors. In particular, experiments using reactor neutrinos are more sensitive to these spectral distortions, as I said, at low energies, and therefore allow us to set stronger bounds at small mediator masses. Similarly, we also considered the case of a light scalar mediator. The difference is that, well, we can also compute here the typical cross-section, but this cross-section is now, there is no interference with the standard model, so it sums up, it sums to the standard model one. And also in this case, the NEUTRINO-NUCLEus process has no typical, not great enhancement in the case of the light mediator. So the inclusion of these NEUTRINO-NUCLEus events does not affect the final result. And indeed, again, having a look at the 90% confidence level exclusion bound that we obtain here from the combined analysis of the two coherent data sets, we see that indeed the bound is flat at low mediator masses. And we see that an experiment using reactor neutrinos, like the case of Dresden, would allow to improve by up to 1 order of magnitude these bounds at mediator masses below the MeV scale or so. So there is really a big complementarity between these facilities, and therefore it's really interesting to have results from both of them to get most of the information, both concerning standard model and BSM physics. Now, I don't know if I have still some time. I think maybe 10 minutes or so.
Yeah, you have time, flexibility.
Okay, thanks. So I would like to discuss some other implications of CEvNS concerning Darmeder. And actually, one of the motivations of CEvNS is also that it is interesting also for the dark matter community, in the sense that CEvNS is a very relevant background for these dark matter experiments. So let me just quickly introduce direct WIMP searches. Well, we know that if dark matter is made of particles like WIMP that interact with the standard model particles, then we can try to detect it. And one of the strategies that have been envisaged at the scope of WIMP detection is the so-called direct detection, which looks for the energy depositing with the detector by the scattering of dark matter on the target. So direct detection experiments are underground detectors that look for ghostly particles that are neutral or at most merely charged, are weakly interacting, of cosmological or astrophysical origin, and long-lived enough. The scatterings that they look for are rare, if any at all, and therefore a possible observation require an excellent background reduction, large exposures, both in terms of volume and time, and very low energy thresholds if we want to explore also low dark matter masses. So you see that basically these experiments share many technology requirements in common with the CEvNS experiments. The signals that we can expect at these experiments depend on the mass of the WIMP, of the dark matter particle that we are looking for. But for typical WIMPs, signals would be nuclear scattering or electron scattering. Indeed, in general, standard WIMPs or also light WIMPs with masses below or around the GeV scale, let's say, are searched for via elastic scattering of nuclei or electrons, thus leading to a nuclear recoil or an electron recoil as a signature. In order to compute the rates of these WIMP searches, we need to know some astrophysical parameters, in particular the distribution of dark matter in the galaxy, particle physics parameters, at least the particle's mass and cross-section that we expect from the typical dark matter model, and some nuclear physics, for instance, concerning form factors. Actually, already in the 80s, people have pointed out that WIMPs could be searched using the same detectors that have been proposed for CEvNS measurements. And indeed, there is a very big overlap among these two searches. In particular, concerning dark matter nuclei scattering, which are the searches that usually lead to the most stringent bounds, in particular if they are spin independent, because they are also affected by some coherent enhancement. So the current status of these searches is summarized in this figure concerning spin independent WIMP nucleon interactions. And we see that all the colored lines and this green area correspond to the region that has been already explored by different experiments in terms of the cross-section and the WIMP mass. Of course, experiments are continuously improving, and they are expected to test smaller and smaller cross-sections by increasing the exposure and lowering the backgrounds, and exploring smaller WIMP masses by lowering the energy threshold. So soon, these experiments are expected to touch the so-called some kind of irreducible background from neutrinos, and actually they have already touched it this year, a background that arises from astrophysical neutrinos from the sun, the atmosphere, and the diffuse supernova neutrino background. So these astrophysical neutrinos would give rise to fluxes that are shown here in this figure as a function of the neutrino energy, which can be quite sizable, especially in the case of solar neutrinos. And if we compute the expected recoil rates from these astrophysical neutrinos inducing CEvNS, for instance, in a xenon target, which is the typical material used by current experiments, we see how these rates can indeed be large. And we can, the interesting point is that we can superimpose on it the expected rate from a WIMP particle scattering on the same target, a 6 GeV WIMP or a 100 GeV WIMP. We see that the 6 GeV WIMP would mimic almost perfectly the rate that we expect from boronate solar neutrinos, whereas the heavier WIMP would mimic what we expect from atmospheric neutrinos. So the message here is that there are indeed some relevant neutrino backgrounds mainly of astrophysical origin, that induce CEvNS and can produce nuclear recoil spectra that can have strong degeneracies with those that we expect from spin-independent WIMP interactions. So increasing the exposure of these experiments does not really imply a linear improvement in the sensitivities, but rather we expect it to lead to some kind of saturation, which is usually referred to as a neutrino floor. Now, more recently, people have redefined this background as a neutrino fog, and this is a better definition indeed, because we should not think about it as a hard limit. First of all, because it depends on several uncertainties, both on the astrophysical side, but also on the nuclear physics side, for instance, or on the possible presence of new interactions. And also, in principle, it could be overcome if we look carefully at the spectra tails or if we use some other techniques like directionality or so on. I will not enter into details in this because it's really another, would be another seminar, but let me just mention concerning these backgrounds for their direct detection experiments that, well, future experiments, future detectors like the one proposed by the XLCD consortium aims at improving dramatically in exposures and in threshold. So this detector is expected to be to have a volume as large as 100 tons and an energy threshold as low as 0.1 keV, which is of course very interesting because it would allow us to test also low mass WIMPs. So we asked ourselves whether only astrophysical neutrinos would be a relevant background for WIMP searches for this kind of next generation direct detection experiments. And the answer is that probably it's not the case, in the sense that there can be also relevant background from reactor neutrinos. So this map shows all the nuclear reactors that are located close, I mean between thousands of kilometers from 5 big laboratories that could host one of the next xenon detectors. And so we wanted to estimate what is the expected background from reactor neutrinos that could affect dark matter detection experiments if located in one of these 5 sites. So here I'm showing the power as a function of the distance from the detector of all the nuclear reactors that are located, as I said, close to these 5 sites, which are the Gran Sasso laboratories, NOLAB, Bulbi, SURF, and Kamioka. We estimated the differential recoil rate basically through a convolution of the CEvNS cross-section and the typical flux that we expect from nuclear reactors, of course, weighted by the sum of all the nuclear reactors that can affect one of the locations. So this plot shows the differential flux of reactor neutrinos that would affect each of the locations. And here I'm instead showing the differential rate of differential number of events that we expect from reactor neutrinos at these sites in the colored lines as a function of the energy threshold. As I said before, a future detector like XLCD aims at lowering the threshold down to 0.1 keV. So, of course, so this black dashed line is what we expect from boron-H solar neutrinos. So, of course, that dominates for sure at present. So at present, we do not need to care about the reactor neutrinos at all. But in the future, maybe if these experiments really continue to improve in volume and in threshold, then at some point you see that the expected events per year as a function of the threshold at the different sites, for instance, Bulbi, you see it's quite sizable. So still below the solar neutrino background, but also should be included in the estimation, for instance, of the neutrino fog. And finally, very quickly, let me discuss another possible implications of CEvNS experiments, which is the possible production of new particles. New particles could be of several kinds, sterile neutrinos, axion-like particles. In this case, we consider the scenario where we can have a possible production of a new sterile fermion, MeV scale sterile fermion, through the upscattering process of neutrinos of the nuclei and the electrons of the detector material. So basically, we are considering an effective interaction like this one. We have a possible upscattering into some sterile fermion. The effective Lagrangian is shown here. And well, we also here we consider some generalized interactions, but let me now focus only on the vector one. And we also consider the case where we promote the mediator to a light one. So we have this process mediated by a light vector particle. We computed the cross-sections for both the NEUTRINO-NUCLEUS and the CEvNS process. Here you see the cross-section for CEvNS is very similar to the standard model one, apart from the fact that we have an extra term that of course depends on the mass of the produced sterile fermion. So in this paper, we analyzed both the coherent data, in particular the cesium-iodine one, and the data from direct detection experiments, LZ and xenon and ton. In this case, we consider the NEUTRINO-NUCLEUS signature. And we also computed sensitivities for DUNE, for the DUNE near detector, that could also be sensitive to this upscattering. So this plot shows the bounds and the sensitivities in terms of the coupling of the mediator and the mass of the mediator or the mass of the produced sterile fermion. Of course, we have now more degrees of freedom because both masses are free parameters. So we set some benchmarks, some ratios, we choose some ratios among the masses. And let's say the idea behind this analysis was to show that there is complementarity between the different experiments, because, for instance, direct detection experiments like LZ and xenon and ton would set the most stringent constraints at low masses. Coherent would do better at present at heavier masses up to 100 MeV or so, depending on the scenario, of course. And in the future, DUNE would improve even more, in particular testing also heavier sterile fermions that cannot be produced at coherent, for instance, because we have some kinematics limit dictated by the neutrino source. So yeah, the message here was that indeed coherent can also play a role, also in this case, providing relevant information on a possible BSM scenario like the upscattering of a neutrino into a sterile fermion. So I finish here. Let me summarize. Well, in this seminar, I've discussed the CEvNS process. At the beginning, I discussed the main characteristics, the main features of this process, in particular the coherency condition, and the fact that the neutrino sees the nucleus as a whole, as a single particle, and this leads to a typical enhancement of the cross-section. I've discussed which experiments can try to observe it and which ones have already observed the CEvNS. And also I have then discussed some implications of these CEvNS observations, in particular from the analysis of coherent and the Dresden 2 data. Among the implications, I've discussed both standard model physics and BSM scenarios like new interactions, the production of new particles, and so on. I've also quickly commented about the impact of CEvNS on the so-called neutrino floor or fog, so on Darmstadt searches. Concerning the results that I've shown based on the analysis of coherent data, basically the main message is that the inclusion of the recent cesium-iodine dataset significantly improved the sensitivities in most of these cases. And this was expected because indeed that dataset has more statistics. So we are really waiting for a wealth of information that is expected from forthcoming data, not only from upgrades of coherent, but especially from reactor experiments, because as I said before, these facilities are really complementary. And so all this data will have very relevant implications for both standard model tests and for searching for new physics in the neutrino sector. So I thank you very much for the attention, and if you have questions.
Thank you very much, Valentina, for the very nice and very complete talk. Question from the audience? Any questions? Yes, Claudio, please go ahead.
Yeah, I have a question. Very nice talk, Valentina.
Thanks.
I suppose that the probability of having this coherent scattering depends on the nucleus, right? I mean, I suppose for nuclei which are more, bound together, so say they have a higher binding energy, it should be more likely to have this this kind of scattering than with a loose bound nucleus. Is there some intention to test this kind of hypothesis?
So in general, I would say that the main ingredient that is relevant is indeed if the targets are heavy or not, if these nuclei are heavy nuclei or not, right? Indeed, because you have this enhancement that depends on the mass of the nuclear target. On the other hand, for instance, for larger masses, the recoil energy is a bit smaller. So you have to find a balance between if you want to enhance indeed the cross section, or if these still lead to an observable recoil. Then I don't know. I mean, if you mean other. I mean, concerning nuclear physics is of course probably the most the least known part of this cross section, So it depends if you consider. I don't know if your questions was more related to this or if it was related to some other. Okay, so I mean
Because say if you have if you have a heavier nucleus, you have more particles inside the nucleus. Of course, the scattering is larger, but the problem is what's the fraction of the elastic, nuclear scattering compared to just collision to anything. And that I would imagine is more likely if the binding energy of the nucleus is higher.
Yeah, I mean the transitions to the incoherent inelastic process.
Exactly.
It's indeed it's complicated actually, and it's complicated to compute. I'm not expert of nuclear physics, so I know that there are few works that have tried to compute it, really trying to compute all the nuclear parts in detail. Some of them were relying on some assumptions and claimed that there would be a smooth transition from the coherent elastic to the incoherent inelastic, but I think at present is still not so clear. In any case, of course, if you stick to neutrino energies where you can expect the process to be really fully coherent and elastic, that would be, of course, the event rate would be much larger, no? That the incoherent inelastic contribution would be subdominant. So,
right. Yes. Thank you.
I hope I answered. Yeah, thanks.
Yes.
More questions from the audience?
I have one. Yeah. Couple. Great talk, Valentina. Thank you.
Thanks.
So you, in this case of scattering, how much you think one can gain information from adding the direction of the spectrum on top of what on top of the recoil spectrum?
Okay, good question. Let me think. If you have some, I don't know. I mean, because what you're looking here, it's really the scattering. I mean, you have information. You are looking at the spectra from the scattering really within the detector, right? It's not like what you are assuming is that you expect a variation in your recoil spectra due to the fact that some of these neutrinos, instead of remaining neutrinos in a finer scale, upscatter to something else. So using directionality, I don't know, maybe you can gain something, but I'm not so sure. I mean, I would expect that directionality helps more when you have, for instance, I don't know, the production of a new particle already at the source, like lidar matter, that you produce from, I don't know, like the pions and so on. And so you expect already some new particle that would also induce some scattering inside the detector, but that comes with different properties compared to the neutrinos. But I don't know. I'm not sure. I mean, this is my guess, but maybe, I mean, of course, the more information you add, the better it is in general. So, well, depending, but hopefully we can extract.
Because I was wondering that if you have a massive state, so depending on the mass of that final state particle, you would expect somehow the angular distribution to change, right? So it will be like you know, the directional spectrum will change upon the values of the fermion that you have in that final state. So I had expect that to probably provide further information. Because I don't know how much the recoil spectrum differs when I take that massive state to have a mass equal to 0. So if I calculate the CEvNS, you know, spectrum standard one, and I compare with the upscattering, how much can I tell the differences between the two recoil spectrum?
Yeah, I mean, when the mass of the sterile fermion that is produced goes to 0, you basically are in the standard situation, right? And indeed, actually, the cross-section, you recover exactly the CEvNS cross-section and so on. So even the bounds at some point, indeed, the bounds that we obtain from this analysis, from the scattering, do not change anymore if we put masses of the sterile fermion that are small enough below some value. So maybe, as you say, yeah, indeed, in that case, having some information on the angular distribution can help. The other thing that we also considered was the possibility that this guy decays inside the detector. So that, of course, also gives some additional information that you don't have from the neutrinos, right? So, but yeah, of course, I mean, it's a good point. Probably would be interesting also to check that with the directional detector,
Yeah. Okay. So, and I have a last question. You probably remember that paper written by Concha and Pilar and their students. They were using Borexino data, right?
Okay.
So they argue that if you have non-diagonal NSI, not flavor, not lepton flavor, non-diagonal NSI, then you cannot anymore properly define the flavor basis. And so since you cannot define anymore the flavor basis, then what they argue, and I kind of agree with that, is that that the standard procedure that we used for the calculation of event rates with non-standard neutrino interactions is not anymore suitable, that you rather have to rely on the density matrix formalism. And it turns out that they did that in that paper. Do you have an idea of how much, you know, the departures of these fits with NSI differ when you take that path rather than doing the standard thing that we have been doing for quite a while?
No, I cannot now say. I don't remember exactly, so I cannot say how much. But yeah, it's a good point. It's an interesting point. I mean, they did several work on that, no? Also combining. So of course, combining. I mean, not only CEvNS data, but also in general global fit neutrino data. So from different experiments. So.
Yeah, but so the one I'm referring to is the one that he wrote last year, 2023, for Borexino data. Yeah. So for the others, you know, Concha as well, you know, did analysis, you know, in the standard way. But then in that paper, they are pointing out that if you add flavor of diagonal couplings, then you cannot anymore define the flavor basis, right? So properly define that. So you have to rely on. So basically, flavor states are not anymore like proper states for the description of that scattering process, and so they argue that you have to rely on that. And I think I kind of agree, but what I'm not entirely sure whether that probably is overkill, you know, because you know beforehand that this NSI parameters cannot be order 1. You know, it's order 10 to the -2. Yeah. So okay, it's probably an effect which any experiment will be capable of telling you. Probably you are correcting the bound by at the per mil level, right? And then you don't have an experiment capable of resolving that. Even you know, a 10-ton liquid argon detector, we won't be able to do that. So that is my guess, right? But just asking whether you had some idea on that.
Yeah, no, at present I cannot comment much because I don't remember. Well, I will check. I will check the paper.
Okay. Thank you very much, Valentina.
No, thank you, thank you.
There is a comment from Boris. Boris, please. Boris just mentioned that he has a comment. Boris? Any comments? Any more comment or question from the audience? If there are no more comments or questions, we thank Valentina for the very nice and very great talk. Thank you so much, Valentina.
Thank you again for the invitation. It was a pleasure.
And we meet at the next seminar.
Thank you.
Thank you very much.
Thank you very much.
Thank
Okay.
you.
Bye
Bye
bye.
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 Bye bye.
Bye bye.
Bye.
Bye bye. Thank you.